In this lecture, we will discuss the control rectifiers. The diode rectifiers provide a fixed output voltage only. To obtain controlled output voltages, phase control thyristors are used instead of diodes. The output voltage of thyristor rectifiers is varied by controlling the delay or firing angle of thyristors. A phase control thyristor is turned on by applying a short pulse to its gate and turned off due to natural or line commutation, and in case of a highly inductive load, it is turned off by firing another thyristor of the rectifier during the negative half cycle of input voltage. Three-phase controlled rectifiers are simple and less expensive, and the efficiency of these rectifiers is above 95%. Since these rectifiers convert from AC to DC, these control rectifiers are also called AC to DC converters and are used extensively in industrial applications ranging from fractional horsepower to megawatt power levels. The phase control converters can be classified as single phase or three phase. Each of these can be subdivided into semiconductor, full converter, and dual converter. A semiconductor is a one-quadrant converter and it has one polarity of output voltage and current. A full converter is a two-quadrant converter and the polarity of its output voltage can be either positive or negative. However, the output current of full converter has one polarity only. A dual converter can operate in all four quadrants and both the output voltage and current can be either positive or negative. So let us discuss the single phase full converters. The circuit arrangement of a single phase full converter is shown in figure A with a highly inductive load so that the load current is continuous and ripple free. During the positive half cycle, thyristors T1 and T2 are forward biased, and when these two thyristors are fired simultaneously at omega t is equal to alpha, the load is connected to the input supply through T1 and T2. Due to the inductive load, thyristors T1 and T2 will continue to conduct beyond omega t is equal to pi, even though the input voltage is already negative. During the negative half cycle of the input voltage, thyristors T3 and T4 are forward biased, and the firing of thyristors T3 and T4 will apply the supply voltage across thyristors T1 and T2 as reverse blocking voltage. T1 and T2 will be turned off due to line or natural commutation, and the load current will be transferred from T1 and T2 to T3 and T4. So the figure C shows the waveform for input voltage, output voltage, and input and output currents. During the period from alpha to pi, the input voltage Vs and the input current Is are positive and the power flows from the supply to the load. The converter is said to be operated in rectification mode. During the period from pi to pi plus alpha, the input voltage Vs is negative and the input current Is is positive, and there will be reverse power flow from the load to the supply. The converter is said to be operated in inversion mode. Depending on the value of alpha, the average output voltage could be either positive or negative, and it provides a two-quadrant operation. The average output voltage, that is VDC, comes out to be 2 Vm upon pi cos alpha, and the RMS value of the output voltage comes out to be same as the supply voltage Vs. With a purely resistive load, thyristors T1 and T2 will conduct from alpha to pi, and thyristors T3 and T4 will conduct from alpha plus pi to 2 pi. We have seen that single-phase full converters with inductive loads allow only two-quadrant operation. If two of these full converters are connected back to back, both the output voltage and the load current flow can be reversed. The system will provide four-quadrant operation and is called a dual converter. So a dual converter are normally used in high power variable speed drives. If alpha 1 and alpha 2 are the delay angles of converters 1 and 2 respectively, the corresponding average output voltages are VDC1 and VDC2. The delay angles are controlled such that one converter operates as a rectifier and the other converter operates as an inverter, but both converters produce the same average output voltage. Figure shows the output waveforms for the two converters when the two average output voltages are the same. Figure C shows the VI characteristics of a dual converter. So the average output voltages are VDC1 is equal to 2 Vm upon pi cos alpha 1 and VDC2 is equal to 2 Vm upon pi cos alpha 2. Since one converter is rectifying and the other one is inverting, so VDC1 is equal to minus VDC2, or cos alpha 2 is equal to minus cos alpha 1, that is equal to cos pi minus alpha 1. Therefore, alpha 2 is equal to pi minus alpha 1. Since the instantaneous output voltages of the two converters are out of phase, there will be an instantaneous voltage difference and this will result in circulating currents between the two converters. This circulating current will not flow through the load and is normally limited by a circulating current reactor LR. If V01 and V02 are the instantaneous output voltages of converters 1 and 2 respectively, the circulating current can be found by integrating the instantaneous voltage difference starting from omega t is equal to 2 pi minus alpha 1. Since the two average output voltages during the interval omega t is equal to pi plus alpha 1 to 2 pi minus alpha 1 are equal and opposite, their contributions to the instantaneous circulating current IR is 0. Calculating for IR, it comes out to be 2 Vm upon omega LR cos omega t minus cos alpha 1. The dual converters can be operated with or without a circulating current. In case of operation without circulating current, only one converter operates at a time and carries the load current, and the other converter is completely blocked by inhibiting gate pulses. The operation of circulating current has certain advantages. The circulating current maintains continuous conduction of both converters over the whole control range independent of the load. Since one converter always operates as a rectifier and the other converter operates as an inverter, the power flow in either direction at any time is possible. Since both converters are in continuous conduction, the time response for changing from one quadrant operation to another is faster. Three-phase converters are extensively used in industrial applications up to 120 kilowatt level where two-quadrant operation is required. Figure shows a full converter circuit with a highly inductive load. This circuit is known as three-phase bridge. The thyristors are fired at an interval of pi by 3. The frequency of output ripple voltage is 6 Fs and the filtering requirement is less than that of three-phase semi and half-wave converters. At omega t is equal to pi by 6 plus alpha, thyristor T6 is already conducting and thyristor T1 is turned on. During the interval pi by 6 plus alpha to pi by 2 plus alpha, thyristors T1 and T6 conduct and the line-to-line voltage VAB appears across the load. At omega t is equal to pi by 2 plus alpha, thyristor T2 is fired and thyristor T6 is reverse biased immediately. T6 is turned off due to natural commutation. During interval pi by 2 plus alpha to 5 pi by 6 plus alpha, thyristors T1 and T2 conduct and the line-to-line voltage VAC appears across the load. The firing sequence is 1, 2, 2, 3, 3, 4, 4, 5, 5, 6 and 6, 1. Figure B shows the waveform for input voltage, output voltage, input current and current through thyristors. Figure B shows the waveform for alpha is equal to pi by 3. For alpha greater than pi by 3, the instantaneous output voltage V0 will have a negative part. Since the current through thyristors cannot be negative, the load current will always be positive. Thus, with a resistive load, the instantaneous load voltage cannot be negative. A three-phase bridge gives us 6 pulse output voltage. For high power applications such as HVDC and DC motor drives, a 12 pulse output is generally required to reduce the output ripples and to increase the ripple frequencies. If the line to neutral voltages are defined as VAN, VBN and VCN, the corresponding line to line voltages are calculated as VAB, VBC, VCA. The average output voltage is found as VDC is equal to 3 under root 3 Vm upon pi cos alpha. The maximum average output voltage for delay angle alpha is equal to 0 is VDM, that is equal to 3 under root 3 Vm upon pi, and the normalized average output voltage is Vn is equal to VDC upon VDM, that is equal to cos alpha. The RMS value of the output voltage is found as Vrms is equal to under root 3 Vm in brackets 1 upon 2 plus 3 under root 3 upon 4 pi cos 2 alpha under root. In many variable speed drives, the 4-quadrant operation is generally required and 3-phase dual converters are extensively used at 2000 kilowatt level. Figure shows 3-phase dual converters where two 3-phase converters are connected back to back. Due to the instantaneous voltage differences between the output voltage of converters, a circulating current flows through the converters. The circulating current is normally limited by current reactor LR. The two converters are controlled in such a way that if alpha 1 is the delay angle of converter 1, the delay angle of converter 2 is alpha 2 is equal to pi minus alpha 1. Figure shows the waveforms for input voltages, output voltages and voltage across inductor LR. The operation of each converter is identical to that of a 3-phase full converter. During the interval pi by 6 plus alpha 1 to pi by 2 plus alpha 1, the line-to-line voltage VAB appears across the output of converter 1 and VBC appears across converter 2. If the line to neutral voltages are defined as VAN is equal to Vm sin omega t, VBN is equal to Vm sin omega t minus 2 pi by 3, VCN is equal to Vm sin omega t plus 2 pi by 3. The corresponding line-to-line voltages are VAB, that is equal to VAN minus VBN, that is equal to under root 3 Vm sin omega t plus pi by 6. VBC is equal to VBN minus VCN, that is equal to under root 3 Vm sin omega t minus pi by 2, and VCA is equal to VCN minus VAN, that is equal to under root 3 Vm sin omega t plus 5 pi by 6. If V01 and V02 are the output voltages of converters 1 and 2 respectively, the instantaneous voltage across the inductor during interval pi by 6 plus alpha 1 to pi by 2 plus alpha 1 is VR, that is equal to V01 plus V02, that is equal to VAB minus VBC. On calculation, it comes out to be 3 Vm cos omega t minus pi by 6. The circulating current can be found from 1 upon omega Lr integration of pi by 6 plus alpha 1 to omega t Vr d omega t. That comes out to be 3 Vm upon omega Lr sine omega t minus pi by 6 minus sine alpha 1. Effects of load and source inductances. In the derivations of output voltages and the performance criteria of converters, we have assumed that the source has no inductances and resistances. Normally, the value of line resistances are small and can be neglected. The amount of voltage drop due to source inductances is equal to that of rectifiers and does not change due to the phase control. If all the line inductances are equal, the voltage drop is V6X is equal to 6F LC for a three-phase full converter. The voltage drop is not dependent on delay angle alpha when under normal operation. However, the commutation or overlap angle mu will vary with the delay angle. As a result, the delay angle is increased, the overlap angle becomes smaller. This is given in the figure shown here. The volt-time integral as shown by cross-hatched area is equal to IDC LC and is independent of voltages. As the commutating phase voltage increases, the time required to commutate gets smaller, but the volt seconds remains the same. If Vx is the average voltage drop per commutation due to overlap and Vy is the average voltage reduction due to phase angle control, the average output voltage for delay angle of alpha is VDC alpha is equal to VDM minus Vy, and Vy is equal to VDM minus VDC alpha, where VDM is equal to maximum possible average output voltage. The average output voltage with overlap angle mu and two commutations is VDC alpha plus mu is equal to VDM minus 2Vx minus Vy. Substituting Vy, we can write the voltage drop due to overlap as 2Vx is equal to 2Fs IDC LC, that is equal to VDC alpha minus VDC alpha plus mu. Thus, the overlap angle mu can be obtained for known values of load current IDC, commutating inductance LC and delay angle alpha. In this lecture, we discussed about the single-phase full converters, the single-phase dual converter, the three-phase full converter, and the three-phase dual converter. And finally, we discussed the effects of load and the source inductance. Thank you.